Okay, I've had a lot of questions about Unit 5, Activity 5, specifically the end of the chapter. Unit 5, Activity 5 talks about chain rule and the derivative of composite function. And a couple of examples at the end of on the last content page, a couple of examples of practical application questions introduce you guys to the concept of optimization with respect to calculus and finding derivatives. So I'm going to work you through a question that I've got starting to get a lot of emails about. I have edited the content page, the answer link, so that makes a little bit more sense. But I'm going to use the video here and allow you guys to see a solution that has a visual with it, a drawing, and I'm going to walk you through a couple of concepts about optimization and finish off the solution with a graph in DESMOS just to validate what we've found here. So let me just open up. You guys are watching. Welcome to this video. I'm just going to open up, then share my screen and open up the question with you. Okay. So first of all, here's the question. It's on Unit 5, Activity 5, the chain rule and applications, and it's on the third content page right here. And it's question number 3 about analytical geometry. It says, consider the circle x squared plus y squared equals 3. Find the dimensions of the largest rectangle that can be inscribed in this circle. So there's a couple of, we require a bit of an explanation here. Okay, so here's the question I have it in my whiteboard. So this is basically what I've got. I've got the constraint of this circle, okay? And the question here, this x squared plus y squared equals 3, I'm going to call in calculus the constraint equation. Okay, so the particular question is always under this constraint. The inscribed rectangle in black, shown in the diagram, is under the constraint that it has to be inside this circle. Okay, and our optimal equation is the one we're going to try and develop, take the derivative of, set equal to 0, and solve. But we have to work this constraint equation in. Okay, so basically the idea is I've got to find the area of this black outlined square here inside my circle, and I want to find dimensions such that I have the largest rectangle. Okay, now in this particular case, largest rectangle, okay, I'm going to assume is maximum volume or area, right? The biggest rectangle I can have is going to be the maximum area, and the key word maximum, okay, you'll also see questions where they're looking for a minimum, okay, are optimization questions, okay, and this is the concept of optimization questions. We're trying to get an optimal situation here, find some dimensions in this case, but use some calculus and some math to find an optimal situation, the best situation. And in this case, I want the biggest area that I could put inside this circle. Okay, got it? Straight? Okay, so here's what we do. Now, before I get started, though, I want to talk about the fact that I could have other rectangles. I could have a rectangle. Sorry, I should do this in black. Okay, I could have a rectangle that was shaped like this. Okay, it's still in the constraint, right? It's still in the constraint of the circle x squared plus y squared equals 3. I could have a rectangle, okay, like this. Okay, and either way, okay, I've got all kinds of different types of rectangles. I'm trying to find one rectangle that gives me the biggest area, and each of these different sized, different dimensioned angle or rectangles, sorry, lead to different areas, right? So that's kind of what I'm looking for. I'm just going to clean this up a little bit so I can. Okay, there we go. Okay, so that's the first thing we do is we use the constraint equation. Use the constraint equation and rearrange it. I'm going to rearrange it to solve for y. I like to work with x's in my functions, so okay, I'm going to and then go the square root of 3 minus x squared. Okay. Now that's solving for y, right? Now, normally in math, it'd be plus and minus, but I'm really looking at, okay, some restrictions on here where x and both y are greater than or equal to 0 because I want dimensions here. Okay, so now I got to look at, okay, that's fine. That should be okay. All right, not a problem. Okay, and in particular, since y has got to be equal to 0, right? I'm trying to find a dimension or a length. My y, okay, is just going to be the positive. I can drop the negative sign here. Okay, now my optimal equation is the one that I want to try and take the derivative of and optimize, and it's where I want to find the maximum area. Right, so let's take a look at the diagram here. The area of this rectangle, okay, that's inside my constraint equation of my circle here, the area of this rectangle, okay, is x and y. Now this side would also be x, right, symmetrical, and okay, this would be 2x. Okay, similarly, this would be y, this would be y. So over here, this would be 2y. Okay, so any rectangle I have in there, if I know the point, right, under this constraint, any rectangle that's going to be inside that circle are going to have dimensions 2x and 2y. Okay, so my area formula is length times width. Okay, right? That's the practical formula that you're used to seeing back in elementary school. In this particular case, as I apply that area formula to my rectangle, I have A equals 2x times 2y. I know that to be mathematically 4xy. So I can find the area by multiplying 4 times x times y, if I knew the dimensions of x and y. As a function, okay, I'm going to write my area as a function of x, and I'm going to replace y with the constraint equation. Okay, and that'll be 3 minus x squared. Okay, so there's my function in terms of, there's an equation for that represents area in terms of one single independent variable. In this case, it's x. Now I've seen students solve for x and use that into y, and that's fine too. Okay, so the next thing we have to do is take the derivative of this function. Okay. Now the derivative of this function is found by using the product rule. So just over here on the side, I'm going to write my two products, 4x and 3 minus x squared, except I'm going to get rid of the square roots and write it as 1 to the 1/2. Okay, so let's take the derivative of both parts. The derivative of 4x is 4, and the derivative of 3 minus x squared to the 1/2 power is 1/2 times 3 minus x squared to the negative 1/2. But this is a chain rule, so I also have to take the derivative of this inside function right here, and the derivative of that inside function is negative 2x. Okay, so now I'm just going to clean this up and bring this all together. When I simplify this, I'm going to have the 2's will cancel each other out, right? I'll have a negative x in the numerator, and I'll have a 3 minus x squared to the 1/2 in the denominator. Okay, so now I can use the product rule and apply the product rule and bring all these pieces together here. So the derivative of my function, oh, I messed that up. Okay. The derivative equation, okay, is 4 times 3 minus x squared to the 1/2 plus 4x times negative x over 3 minus x squared to the 1/2. Okay, so that's the function I'm working with, the derivative function. Now I'm just going to take a line or two here, or a step, and sort of clean this up a little bit. It'll be a minus 4x squared all over 3 minus x squared to the 1/2. Okay, now to find the optimal point, I set my derivative equal to 0. Now there's a variety of ways you can solve for x when you're set the derivative equal to 0. And this will give, the reason I do this is give maximum area here, okay? And I'm looking for, remember that concept of a derivative equal to 0? I'm looking for the slope of the tangent line equals 0, and that would be the high point or the low point on the function. I'll show that function here in a minute, okay? But let's solve this first. Okay, so I've got to set this expression equal to 0. Now there's a variety of ways I can solve this. I could get a common denominator and just work on the left-hand side, right? You get a common denominator, add these together. I could also realize that one of these terms, I've got two big expressions or two big terms, if you like, and one of them is a negative right here. So if I simply just move this term with the negative sign over to the right-hand side of my expression, I'm going to have, okay, and it's going to equal 4x squared over 3 minus x squared to the 1/2. Now I can cross multiply, right? Okay, so if I cross multiply, I'm going to have 4 times 3 minus x squared to the 1/2 times 3 minus x squared to the 1/2, and that's going to equal 4x squared, okay? Or 4x squared times 1 if you like, but we're going to drop that 1 in the next line here. Now look what happens here on the left-hand side. I've got 4, then I've got a common base, 3 minus x squared, both of them raised to the 1/2. So if I have a common base with my laws of exponents, I can add these exponents. So that'll just be 3 minus x squared to the power of 1 equals 4x squared. Okay, that's going to clean this up pretty nicely. Okay, so I have 4 times 3 minus x squared equals 4x squared. Now there's little tricks in grade 12 math that allow us to solve this pretty quickly here. Normally you would just expand this out, and that's fine. You can do that. That's an easy way to go about doing this. Okay, if I expand it out, I'd have 12 minus 4x squared equals 4x. I bring my 4x squared over. Okay, that's fine. I could do it this way as well too. I could divide both sides by 4. When I divide both sides by 4, that leaves me with 3 minus x squared equals x squared. Now I bring my negative x squared on my left-hand side over to my right-hand side. I've got x squared equals 3 over 2, or x equals square root of 3 over 2. Now, square root of 3 over 2, remember, it should be, mathematically, it should be plus or minus, okay? But I'm only interested in the plus, again, because x, okay, has to be equal to 0, right? Because we're talking about a distance or a length of a line. Now, the answer link treats this a little bit differently. Okay, I'm going to rationalize the denominator, so that means I'm going to multiply it by, well, this is really just root 3 over root 2, multiply it by root 2 over 2. It gives me a root 6 over 2, which is probably a better way to deal with this. Okay, so what's y? Now I got to use my constraint equation up here. Way up, way up, way up. Okay. This constraint equation to find out what y is. I know what x is. Okay, so I found x. Okay, x to be root. Okay, or I could use this expression, right? That's fine. So y. Okay, y equals 3 minus. Okay, I can put in either one I want here. It's going to be an x squared. Okay. And I have x squared, right? I have x squared. Okay, that could be 3 over 2. Okay, so 3 over 2. Okay, 3 over 2 is in fact just 1.5. So 3 minus, okay, 1.5. I change my get a common denominator. That'd be 6 over 2 minus 3 over 2. Lo and behold, I get the same 3 over 2 for y. Okay, and we dealt with that already. So y, okay, is also, okay, going through that same process. Okay, look here, right? That's the same as y. So it just turns out that y is also root 6 over 2. Okay, so basically, okay, back to my original diagram here. Okay, so that's what we found. We found x to be root 6 over 2 and y to be root 6 over 2. So clearly, okay, that this inscribed rectangle is in fact, okay, a square. It has the same x and y both have the same dimensions. These dimensions, okay, are 2x and 2y. So my dimensions, actually, I just have to take, okay, I have to double dimensions are, okay, for the length, I'm just going to call that 2x, okay, and that's 2 times root 6 over 2, root 6, okay, and the width, okay, is also 2y, and that's 2 root 6. Okay, so the dimensions are root 6 by root 6 square. Okay, I think that's all I'm asked in the question. What are the dimensions? Okay. Yeah, find the dimensions. Okay, and I just found that. Okay, it's a root 6 times root 6 square. All right, so that's how you solve an optimization question. You use the constraint equation, rearrange it, substitute it into your optimal equation, take the derivative, set it equal to 0, and solve for your independent variable here. I want to take a second, okay, and show this on DESMOS though, because I think it's nice to be able to see this type of thing. Okay, so here's our original circle, okay, and I want to, okay, put in the graph. Now I'm going to leave the graph here, both graphs here for a second, okay, and I want to find, so this is my, in red is my, okay, is my graph for, okay, is my graph for the area function. Okay, and that's 4x times 3 minus x squared. Okay, and that's in red. And then I put in the circle as well too. So the point I'm trying to find here is this one, okay, right here, where there's a flat tangent line, right? So that's the maximum or the high point, the peak of this area function is the maximum area. The area is 6, right? That was root 6 times root 6 is just 6. And that occurs at the point 1.25, and it would occur, okay, at that same point right about here, okay, 1.25 on the circle. Okay, and that's sort of how you see that. I'm just going to temporarily, okay, show that like this. So that point 1.25. Now 1.25 is my x component, and I figured out during the question that x was root 6 over 2. So I'm just going to go to my calculator and verify, okay, the root 6, okay, divided by 2 is 1.225, and that's kind of how you see that visually. Okay, so that deals with, okay, that deals with okay, our particular question here that's works through and introduces, you guys use the chain rule to find the derivative, right, and the product rule, but introduces us to optimization. Now, optimization we'll do in unit 6 and unit 7 a little bit more. Okay, that sounds good. Thanks. If you have any questions, make sure you keep contacting me and let me know. Have a good day, everybody. Bye-bye.